All right, in 14.4, in an effort to condense a little bit, I'm not going to prove the, or sort of not prove, but derive the formula, but I am going to show you where the formula in general comes from, and then if you want to see more details, I'm going to tell you what the page number is where you can find it in your notes. So in Calc 2, we had a method for finding the surface area for a solid of revolution, and that formula, so in Calc 2, that formula for finding the surface area looked something like this. It was the integral from a to b of 2 pi times the function f of x times the square root of 1 plus f prime of x quantity squared dx. That's what we had from Calc 2 for finding the surface of a solid of revolution, which was a lot easier than finding the volume of the solid of revolution. It was a lot easier. So in general, though, what we're going to be doing is we're going to be doing this for the surface area of a volume in two-dimension, or in a multi-dimension. So in general, what this looks like, oops. All right, I will use SA. Your book just uses S, but my S's start to look like my integration symbol, so I'm going to say SA. So this is an integration over our region. We're going to have a square root and we're going to have 1 plus, but what we're going to have is we're going to have partial derivatives that are squared. You'll notice we don't get a 2 pi. You don't have the f of x. Those are going to be taken up in the fact that we're doing a double integral now instead of a single integral. So what we're integrating actually looks a little bit different because of that. And just so that you have it if you'd like to look, the derivation for this formula is on page 9, well, there's 2 pages, 934 to 930, okay, 933 to 934. So if you'd like to see how they came about that very specifically, you're welcome to look at this. And it's also very helpful, depending on what the equations are, sometimes to do this in polar coordinates, okay? So we're going to be using polar coordinates within this section when helpful as well. All right, so we're going to do an example. We're going to find the surface area of the indicated surface. This is the portion of z equals 4y plus 3x squared between y equals 2x, y equals 0, and x equals 2. And as is often the case, a picture of the region is sometimes helpful. So x equals to 2 would be bounded over here. Y equals 0 is my x-axis. And then I've got the graph of y equals to 2x. So that has a y-intercept at the origin and then a slope of 2. So a graph looking something like this. So I'm doing this right in here, right, for my region. On this one in particular, I think rectangular coordinates are just as helpful as anything because I don't have y squared and x squared. Not only that, but not only do I have y squared and y squared, not only do I have y not squared, they don't have the same coefficient either. So even if I had a y squared here without the coefficients matching, it wouldn't be helpful. for polar coordinates. So we're actually going to do this for the surface area with the x coordinates and the y coordinates. So taking a look at my limits of integration, it would be helpful for me to have an equation for my diagonal line written in here. So this is y equals to 2x. Since it's already solved for y, we might as well use that as our limits of integration on the interior of the two integrals. So the y value is going from 0 to 2x, and the x value is going from 0 to 2. I need the square root of 1 plus, and what I need next is I need f sub x and f sub y. Well, I haven't actually found those, but they're very clean for this function. What is f sub x? 6x. And even better, what is f sub y? It's what? 4. Okay, good. So I have 6x squared plus 4 squared, and then I did dy first and then dx second. Alrighty. What do we have? What's all underneath there? The square root of what? 17 plus 36x squared. Nice. And this is dy dx. So we need to integrate this with respect to y, correct? So let's do that real quick. I promise we've got about 2 minutes left. Can you guys bear with me for that just a moment? Do you mind? Okay. What's the integral of this with respect to y? Y times that. And I'm supposed to evaluate this at 2x and 0. When I evaluate 0, what happens? It goes away. So the evaluation at 2x is the only piece that matters. Oops. So I have 2x times the square root of 17 plus 36x squared dx. Now, when I integrate this with respect to x, what's going to happen? I mean, what do I need to do in order to integrate this with respect to x? Going to need a u substitution. What would you like to let u be, Caleb? That sounds good. What would du be? $72x? Yeah? And I have a 2x in my problem, so I'm not going to divide by 72. I'm just going to divide by 36, because that will leave me with 2x dx on the right. So I can replace the 2x dx with the du over 36. So I end up with 1/36 integral from 0 to 2. I have the square root part, so I'm going to write that as u. Oops, let me leave my limits of integration off since I'm in u now. U to the 1/2 du. So the 2x, the dx get replaced by the 1/3 over 36 in the du. Very nice. 1/36. What's the integral of u to the 1/2? 2/3 u to the 3/2. So the 2/3 times the 1/36 become what? Yes. (1/54). And the u value is actually supposed to be 17 plus 36x squared, which I'm then evaluating from 2 down to 0. What did I miss? Oh, I missed the exponent. Thank you. 3/2. All right, so let me cut to the chase for you. This actually ends up giving you 1/54. If you evaluate this one at 0, you don't get 0. If you evaluate it 2, you get 161 to the 3/2. And then if you evaluate at 0, you actually get 17, of course, to the 3/2. So this is one version of the answer. This would be the exact version. And then the approximation would be 36.5327. So the calculation for these in this particular section look very much like when we were doing them in Calc 2.